Hi, welcome to another 8-bit computer video. I've got the trusty Heathkit H8 sitting next to me, and this time I'm going to interface a Raspberry Pi to it. Now, I've actually interfaced Raspberry Pis to the H8 before. I've done it by seizing control of the bus with a hold cycle, but this time I'm going to do something different. I'm going to make the Raspberry Pi look like a plain, ordinary 8-bit I/O port with traditional read and write semantics on this computer. And the reason I'm doing that is because there's an application on this that uses a Vinculum VDIP1 module. I wanted to do that, but I couldn't get my hands on a Vinculum VDIP1 in time. They're on back order. There is a substitute part, but it's still going to take a few days to get here, so I decided I would emulate that chip with the Raspberry Pi. So if you want to see one way to integrate a Raspberry Pi with a vintage computer and make it look like a vintage peripheral attached to the bus, go ahead and watch, and then at the end let me know if I did it right or not. Okay, how this project came about, it had to do with my H8 computer, which if you've been watching my channel, you've seen I've done a couple of videos on the H8 so far. I'm having a lot of fun building boards for it. But one of the impediments I've had is transferring files to it. There are a couple different mechanisms. The first is that you could create a disk image and put it on something like a Gotek and try to read it, but I have had almost no luck with that. And the reason because this thing is using an H17 hard sector controller with an emulator, and the Gotek, I've just had hit or miss luck getting the Gotek to do hard sector. I've tried the HXC firmware, works with some stock images, but not the images I created myself. I've tried the flash floppy firmware, couldn't get that to work on the Gotek. So that mechanism was not working for me. The other way to do this is a program called H8D Utility, where you can transfer things over serial and then burn them to a floppy on the computer. Thus, you can create a decent floppy image without having to worry about all the peculiarities of hard sector formats on a Gotek. But that also was kind of hit or miss. I could get that to work sometimes, but I kind of had to swap out the boards in the H8 computer. And then I came across this project by Norberto Collado. Now, Norberto is a member of the Society of 8-bit Heathkit Computers. He's designed numerous boards. I think I've featured them, a couple of them already on my channel. And I have actually built one of the variants of his H17 controller board. And what I've been ignoring until this point is it has a provision for this thing here. This USB looking thing here plugged into it. This is a Vinculum VDIP1. Has a provision to hook that up, and it can talk to it through an 8-bit port, and it can retrieve files off of a USB thumb drive. I don't know, this cable, maybe he's just got it going out kind of like sticking out the back of the case or something so he can plug his thumb drive in. But anyway, you can use this VDIP1 module and you can transfer the files. Now, another SEBHC user, Glenn Roberts, he wrote these VDIP utilities. These are the two utilities that let you work with this Vinculum module. You can change directories on the USB flash drive. You can get a directory. You can get a file. You can put a file. You can communicate. Sort of interactively talk to the firmware. And there's a version of the pip program, letting you do wildcards and stuff like that. So he's got this whole thing here. It talks about how to use this. Great instructions. There's actually, let's see if I can find the back button. There's source code for all of it here. It's written in C. It runs on the H8. And this would allow you to use that Vinculum module to get files off a thumb drive. And that would be an awesome way for me to get files to that H8 computer, so I'm no longer worrying about floppies or worrying about serial transfer. We use that Vinculum module. So I went to go order a Vinculum module. I went on to Mouser. And it says this, 0, notify me when they're in stock. Well, they're coming in a couple weeks. I'm not a patient person, so I wasn't going to wait. And, I have a little bit of a doubt that they're actually going to come because other suppliers, they've got none of them on order. This thing is actually about 15 years old. So, I mean, maybe they show up in a couple weeks in March, maybe not. I don't know. Another option is the V2DIP1-48. This is a newer version of the module, 48 pins instead of 24. Can actually be done in a pin compatible way. About $30 a piece for those. So I did actually go ahead and order myself a couple of those. I'm going to put those on the board, do my USB transfer. It was kind of a holiday weekend, and I kind of wanted to, do something with the computer. So What am I going to do? I mean, am I gonna wait a few days for the V2 dips to show up? Am I going to wait a couple of weeks for the VDIP1s to show up? No, I'm going to come up with a way to emulate this VDIP1 module with a Raspberry Pi. Vinculum VDIP1 module. Yes, from 2010, last updated, so it's about 13 years ago. There's a close-up picture of it. Let me just, there's the pin out of it. Fits a 24-pin IC socket. Going down, going down, going down. Let's find, this is the interface that Norberto and Glenn used, is the parallel FIFO interface. So I looked at that and I said, this doesn't look too bad. So there's 8 data bits. It, reads and writes 8 bits at a time. Put it right on your computer bus. And then it's got a read strobe and a write strobe. Just like any other I/O device that'd be on your vintage computer. You read from it, you write to it, and it's got 2 feedback bits. The RXF bit that tells you when a character is waiting for you. The TXE bit that tells when the Vinculum can accept a character. So I said, well, that looks simple. I mean, I could hook that up to a Raspberry Pi. So, what about the protocol? Let's take a look at the protocol. So here we go. What does it look like? Let's find something like getting a directory. That ought to be simple. Let me just scroll. There's lots of stuff here. If I could just get to the dir command. Like, here's the dir command. Directory command lists the available files in the current directory. The command is simply dir. It's ASCII followed by a carriage return. And it sends back a list of files. And then a prompt when it's done. I mean, that's simple. I can easily write a Python program that will implement this protocol. If we were to look at the commands for reading files, they're also very simple. You open a file and you start reading bytes from it. You can change directories. It's just a cd command, which is either a subdirectory name or ... to back up a level. This is about this Vinculum VDIP thing it's about as simple a way to interface with a USB flash drive as you could possibly have for an 8-bit computer. I can see why Norberto and why Norberto and Glenn chose this thing. So what I'm going to do is I'm going to take and I'm going to rig up my Raspberry Pi so it can emulate that interface, and then I'm going to write a Python program that emulates this protocol, and then I'm going to be able to transfer files to my H8 computer. So let's go ahead and see it. Okay, let's take a look at the project. So I kept this very simple because my intent was to build this on a piece of proto board. So I was too impatient. I didn't want to wait to design something to have it shipped from China. So I just went ahead and sort of set this up with 3 ICs and some resistors. So what we'll have the VDIP1 over here on the left side. And then we'll have the Raspberry Pi on the right side. So you can see I have marked down the GPIO pins that I intended to hook this up to on the Raspberry Pi. It really doesn't matter, you can pick whatever GPIOs you want, though I did choose to make the data bits contiguous because that seemed like that would be handy. Then over here on the left is what is on the VDIP socket. As we went over, there's, data pins, a write, a read, and then these here are the 2 feedbacks. So you might think you could just hook this up to the Raspberry Pi and sort of bit bang this directly, just hook the GPIOs up to the bus and read it. But I don't think that would work, at least not if you're running Linux on the Pi, which you probably are. And the reason it probably wouldn't work is these pulses here are very, very short. So, think about this. When the H8 goes in to do a write, it's going to pulse this for, I don't know, a microsecond or two. It's going to put the data bus out there, pulse it for a microsecond or two. Our user mode Python program, it's not going to catch that. So what I did here is I used a latch. Standard 8-bit latch. The latch is clocked on the rising clock pulse, so it's clocked when it goes from 0 to 1. And there's an output enable, this OC. So what happens, the computer comes along in here and it does a write, which will clock in the data on the data bus into this latch. Then when the Raspberry Pi wants to come read it, regardless of what the computer's doing over here, it can pull down this RDPI, read from Pi, which will enable this output, and send the data out here to the Raspberry Pi. Now you'll see there are some resistors here. These are 5-volt devices. The H8 is a 5-volt computer. The Raspberry Pi is a 3.3-volt computer. So hooking these GPIOs up directly, you could damage the Raspberry Pi because you'd give it a 5-volt input to a 3.3-volt chip. So the recommended approach is to set up a resistor divider, a pair of resistors, one here, and you can divide this 5 volts into about 3.3 volts. So I think what I used is just out of the junk box, I used 750s here and 1.5Ks there. So that makes all of these things safe. Now in the opposite direction, another latch, you'll notice I flipped it upside down. It's going the opposite way. So the data comes into this side of the latch, goes out on that side of the latch. So when the Raspberry Pi wants to write something, it'll put its data out here in the data bus. Then it'll come here and it will strobe this clock. It'll go, from high to low, back to high again. So on the low to high pulse on the clock, this latch will ingest whatever this data is. And it'll hold it there until the H8 asks for it. Now that data is sitting in the latch, Pi can go about and do its normal business. And then over here, the H8 computer can come in and do its read, enables the output. This flows onto the H8's data bus. The end of the read disables the output. So all of this works great. These are, 2 latches working in either direction, connecting the Pi to the H8. Okay, so now let's talk about these 2 feedback pins, the TXE and the RXF. So the TXE, according to the VDIP manual, it needs to be low whenever the transmitter is ready to accept a character. So this is basically a low signal that says, vintage computer, you can write and you're not going to be overwriting the buffer. So you want that to be low when you can write to the buffer. You want the RXF, you want it to be low when there is a character in the receive buffer. So this is saying, I put a character there, you can go ahead and receive it. So we need to implement those 2 lines. And we can't just bit bang this from the Raspberry Pi, because the moment this, the H8 computer, the vintage computer, the moment it writes into this latch, we need to set TXE high. Otherwise, the computer's going to, if it sees TXE is still low after it wrote into that latch, it's going to say, hey, that latch is empty and I can keep writing. So to do the handshake, the minute we do this right, we need to flip this bit. And similarly, the minute we do this read from this, we need to flip this feedback bit so that it tells the vintage computer that, hey, the receive buffer is now empty until the Raspberry Pi comes and fills it up. So what I did is I used a 74 HCT 74 flip-flop. Flip-flops are good because you can easily set them and reset them. So when the write occurs, we go in here, we do the pre bit here in the flip-flop. What this will do is this will preset the flip-flop to a 1. So when a write comes in, you set this to 1, which sets this flag out here to say the transmitter is no longer empty. Okay? Similarly, with the read, when we do a read, it sets this pre here, which will set this flip-flop to a 1, and we'll say, hey, the receiver is now no longer full. Either of those work. Then we need to be able to reset them from the Raspberry Pi. So over here, I've given the Raspberry Pi an option to clear this flip-flop. I called it WCLR. And what we do here is it triggers a clock. So on a 0 to 1 pulse, it will clock in whatever's on the D line, so which happens to be ground, happens to be a 0. So in the Raspberry Pi, so after a character has been written, the Raspberry Pi comes up here, reads a latch, and then it goes down here, it toggles this bit up and down. And on the 0 to 1 edge, it will reset this flip-flop, and TXE will go back to low, letting the vintage computer know it can write another character. Now, similarly, with the receive circuit, when the Raspberry Pi puts a character in here, ready for the vintage computer to receive, it will go down here, it will toggle this clock. On the 0 to 1 edge of the clock, it'll clock in this 0, and this status line here will go down to 0, letting the vintage computer know that we put that character in there. And then the vintage computer comes in, reads the character, Read will preset this, goes back to 1. So just like that, flipping the flip-flop back and forth, we'll do our handshake. Finally, the last thing to do is to make sure the Raspberry Pi has a means to query the status. So for example, the Raspberry Pi would like to know that the vintage computer, that it wrote a character into there, so that we can know to go retrieve the character. So what I did, I wired another GPIO up to the TXE line so that we can sense that from the Raspberry Pi. And just like we did up here with the resistor divider, I put a resistor divider down here, 750 and 1500, to take that 5-volt signal, convert it down to 3.3 volt. And same thing for the for the receive line. So that is how I implemented this kind of asynchronous FIFO between the Raspberry Pi and the H8 computer, using this Vinculum VDIP1 protocol. This is something I always wanted to do. I've always wanted to put a Raspberry Pi on a vintage computer bus and make it look like a plain, ordinary I/O port, and I did that. I finally had a use case where I needed to do that, so here it is. Okay, so here is the completed project. So over here I've got my Raspberry Pi, this nice aluminum case. Then I've got a mass of wires that comes over and hooks to this piece of proto board. And on this proto board, we've got the two 74 HCT 574s, the two latches, and the 74 HCT 74 flip-flop down there. There is a bunch of resistors glommed in there. There's a resistor, a SIP resistor, that do these various dividers for the voltage level shifting. Usually I order a PC board from JLC PCB and I make something up like this kind of nice, but this one I had to kind of make in a pinch, so I just assembled it on piece proto board with lots of scraggly wires going everywhere. So Raspberry Pi comes in, hooks up to the right side of the board, pretty much the right side of the schematic. I mean, this board looks exactly like the layout of how the chips were placed on the schematic. At the left side of the board comes this wire here, which hooks down to the into the Vinculum 24-pin connector inside of the H17 controller in the H8 computer. So I just took and I put a bunch of header pins. I used another piece of perf board because I wanted this thing kind of low profile. I didn't want, the long ones that DuPont pins on the wires that stick out. I wanted to make it so it could be low profile, so I've got perf board, this soldered to it, then the wires kind of come up from underneath and solder in. And then we also have this little purple line. So it turns out this circuit needed an active low right strobe, but the right strobe that is on the Vinculum socket is an active high right strobe. Kind of weird. But what I did, rather than adding another 7404 inverter, I ran a wire down here to a spot on the H17 controller where I knew there was an active low right strobe, and I just borrowed that. When I go make this up permanent, we'll do away with the little pigtail wire here, and we'll add an inverter to the circuit. So anyway, that's it. It just plugs in and good to go. Okay, now to attach this, I'm just going to drag this out of the way here. We just need to take the piggyback connector I made. We'll hook it down here to the Vinculum socket, taking care to line up the pins correctly. There, we've got that plugged in. And then the little pigtail here for the right strobe is hooked up to a pin down. Okay. Then I just let the adapter board kind of sit back there. And I toss the Raspberry Pi down here behind the computer. Not the cleanest thing in the world, but it'll suffice for now, and I'll be able to transfer files using this. So let's give it a shot. Okay, let's do a quick demo. So over here on the left, I'm logged into the H8 computer. If we do a directory, takes a little bit to do a directory on the H8 because it's actually running off an ordinary old floppy drive. We could see a bunch of files in here. I'm going to mount the second floppy. It's on SY1. And over on SY1, We can see the Society of 8-bit Heathkit computers, the VDIP utilities that Glenn Roberts wrote. They're sitting there ready to use. So over here on this side, I'm going to run make serve. This right side here is my Raspberry Pi. So I'm going to run my VDIP server. So we'll start that up. And then here we can, we'll do an sy1 colon vdir. That will get a directory. And when I type this in, you will see, the H8 doing its stuff on the left, and then you'll see some debug output from the Python program on the right. Takes it a minute to actually load the program off the floppy. And there we go. So it's actually, what it's doing is it starts up in the directory the software was running in. So that's its default directory. It's just sitting there. So we actually have vdipcmd.py. That's the Python program that ran over on that side. And we can copy these files across. So let me do a sy1 vgit, and then we'll make this. How about? Well, let's do the readme.md. So there we go. It's starting to do a file transfer. It transferred it 256 bytes at a time, and then did the final 70 bytes. So if we do a dir over here, we will see that, yes, the README is there. And there we go. That's my README. Looks like it more or less transferred correctly. There's also a CD command. So let's see, sy1 vcd lib. That's one of the subdirectories that's sitting over there on the Pi. There we go. So now we're in the lib directory. Let's go back to the root. Vcd ... ought to work. And then finally, let's do I think I have a file here called foo. We'll do a vput foo. Hold on. Let's do sy1 vput. I can't type today here. Let me just get a new prompt. Vput. By the way, the oddness when you backspace, that is because this HDOS is currently set up for teletype, which didn't have a backspace. So when you backspace, it actually sort of reprints the characters that you would be over the top of. Kind of weird. Until I flip that bit and put it back to normal, it's kind of hard to read and work with. But anyway, let's do a sy1 vput foo. Yep, so it copied 768 bytes, file called foo. And there you have it, so working as expected. Okay, in conclusion, that's it. That shows it works. You've seen my technique for doing the interfacing with a couple of latches and a flip-flop. Let me know if that's the right approach, or if you've got a better idea or something else that worked for you. Thank you. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and Sandrail stuff. Bye.